Hello again. More physics. Very cool. Oh, and I didn't check to see if I had any chalk before I started. 1 second. Well, that was embarrassing. Okay, so in the last few lectures, we've been talking about electric forces and we talked about electric fields. I tossed in electric field diagrams and electric field vectors, and then I wandered off into electric dipole moment and torques. Oh God! And so a lot of stuff, and concluded what you have probably already figured out for yourself is that this stuff is hard. Okay, and doing the calculations is hard. And my goodness, Kevin, isn't there an easier way? And there is. And to introduce that new idea and that new approach, let's go back to our good old standby, the simplest possible charge configuration that will give us an electric field, and that is the field of a positive point charge. So I have a positive source charge there, and I will sketch its field here. As I've said before, the idea is to sketch as many field lines as you need to make it clear what the field is doing at any particular point in space. Anyway, we've seen this before lots of times. And what I want to do now is think about what would happen if I were to take a negative charge, which I guess would be a test charge, take a negative charge and put it somewhere near this positive source charge. Well, so if I put it there, for example, well, you know what would happen. If I took it there, held it there for a second, and I've looked around, holding it motionless, and then let go, what would happen to it? Well, I hope you immediately say it's going to experience a force that will attract it toward the positive source charge, which, by the way, I've said this before, but I haven't said it for a while, so let me remind you. We are going to assume, just for the sake of not getting too complicated, that our source charges don't move. Our test charges will move, but our source charges are somehow glued down or nailed in place or something so that they don't move. In any case, with that assumption, then our negative charge will feel a force that will attract it towards the positive source charge, accelerate downward toward it, and as it accelerates, of course, its velocity changes, its velocity increases, so it gains more and more velocity the farther and farther it falls. And it doesn't really matter where in the field I put it, but I'm going to, for the sake of my present argument, always start the charge at the same linear distance from the source charge. But if I placed the negative charge initially motionless anywhere along here, exactly the same result would happen. And in particular, once the negative charge fell this distance, its change of velocity would be the same no matter which one of these positions I had chosen to start it from. Okay, and indeed, I could have put it here or here or here or here, and I think you're getting the idea. Indeed, I could have started the charge anywhere along that perfect circle, and the velocity that the negative charge would have obtained by the time it reaches the positive source charge, that change of velocity would be the same in all in any one of these cases, in all of these cases. All right? And, because why not, suppose I had instead started the negative charge this close to the source charge, then all the same thing that I just said would still be true. It would accelerate toward here, would gain some velocity, and the same would be true anywhere along that circle there. However, there will be one difference. There is a difference, and that is the distance that the charge has to travel before it reaches the source is obviously much smaller in this case. Therefore, it accelerates for less time. Therefore, it gains less velocity. Okay. So it starts out with zero velocity here. It ends up with some comparatively small amount of velocity by the time it reaches here. Comparatively small compared to what? Compared to the amount of velocity it gains if instead it had started from way out here. Okay? And if this is confusing you, then really this is nothing more than exactly the same thing as what I mean when I say if this eraser here starts this high above the ground, initially motionless, and I drop it, okay, it gains that much velocity. But on the other hand, if I start it from way up here and drop it, it gained more velocity in that second fall than it did the first fall, simply because it had more distance to travel, more time to accelerate. Well, that was that. Let's try that again. And even higher off the ground. Okay, so hopefully that's clear enough. I'm going to repeat a lot of these arguments, except now I'm going to analyze these from the point of view of energy, work and energy. Okay. Remember work, force through a distance. We're going to go through all this in mathematical detail later. But for now, work is force times distance. An object moves some distance, and the reason that it moves is a force is acting on the object. The force acts on the object, the force causes the object to move. As a result, there's work done on the object. And the next part of that is that the work energy theorem, which is if you do work on an object, you change the object's kinetic energy, or you change the object's potential energy, or possibly both. Okay. In this case, if I put it here, if I start it here, it starts out with zero velocity, which means it has zero kinetic energy. And then I release it. There's a force acting on it, a force of attraction, electric force, pointing that way. The negative charge will move this entire distance. Okay, so, and a force will be acting on it that entire distance. So there's a force pointing, there's a displacement happening, therefore work is done. What effect does that work have? Well, the object started out with no kinetic energy and ended up with a lot of kinetic energy, so the work changed how much kinetic energy the object had. Okay. But in direct analogy with my holding the eraser up in the air, now you know that the eraser right now has some amount of potential energy, or to say that more carefully, it has some amount of gravitational potential energy. Okay? And it doesn't have any kinetic energy, but it does have potential energy. And the work that gravity does as the eraser falls converts that potential energy that it had up here into a lot of kinetic energy that it gains by the time it hits the floor. Well, exactly the same ideas apply here. This charge that I'm holding in place, it doesn't have any kinetic energy right now, but it does have potential energy for exactly the same reason that we said that the eraser that I just dropped had gravitational potential energy. Only the charge here has electric potential energy. And it has that as long as I hold on to it. But as soon as I release it, the gravitational force, the electric force starts to act. We're going to ignore gravity here. The electric force starts to act. The electric force does work on the negative charge, converting its potential energy into kinetic energy. And just like, finally, the last concept, just like energy is conserved when I drop the eraser, that is to say, the amount of kinetic energy that the eraser obtained by the time it hit the floor, the instant just before it hit the floor, that amount of kinetic energy must be exactly equal to the amount of potential energy it started with. Okay, so it starts out with, I'm going to make up a number here, 10 joules of potential energy. When it hits the floor, it has 10 joules of kinetic energy, and that potential energy was converted to kinetic energy by the gravitational work. Similarly, this charge starts out with, I'm making up numbers, 10 joules of electric potential energy. It ends up with 10 joules of kinetic energy. There's only one kind of kinetic energy, 1/2 mp squared. And the conversion from potential to kinetic was accomplished by the electric force doing electric work on the charge. Okay? Finally, these circles, any point on this circle, I put the electron or put the negative charge, I should say, anywhere on this circle, it will have the same amount of potential energy anywhere on this circle as it has anywhere, any other place on this circle. Okay? Similarly, the amount of potential energy that the charge has at this distance from the source is whatever it is. Let's say it's 5 joules. Again, just making up numbers. It has 5 joules of potential energy here, 5 joules of potential energy here, 5 joules of potential energy here, and so on. So every point on this circle represents the electron, the negative charge, having potential energy of 5 joules. So it's an equal potential energy everywhere on this circle. It's an equal potential energy everywhere on this circle. But of course, the potential energy represented by this circle is different from the potential energy represented by this circle. And I don't have to draw just 2 of them. I could draw that circle, or I could draw that circle. And what we have are circles, or as we actually say in the business, lines of equal potential energy. These lines represent points in space that have the same amount of potential energy as every other point on that same line. Okay? It's worth pointing out at this moment that these lines are not actually lines. They are imaginary spherical shells. They are 3-dimensional, just like the electric field is 3-dimensional. And they look 2-dimensional for exactly the same reason that all my drawings of electric fields look 2-dimensional, because I'm constrained to drawing on a 2-dimensional surface. But in fact, if I started out, if I started out at a distance from the source charge here, it would fall in, and so it would start out with 10 joules here and end up with 10 joules of kinetic energy when it reached the source charge. So again, and if I started here, it would fall in with the same change of potential energy and so on. Okay, so imaginary spherical shells. Let me show you another example of this. Back somewhere, some time ago, I drew for you the field of 2 metal plates. I called it a capacitor, and we will study capacitors in some detail later, but for now, just a thin sheet of metal, and I will, now I'll make it a little bit thicker just so you can tell, but usually we always, I guess I really, neglect the thickness of this thing. Again, think aluminum foil or something similar. But somehow or other, and I don't care how right now, somehow or other, we managed to place a continuous distribution of positive charge on this plate and an equal amount and an equally distributed amount of negative charge on the other plate. And when we do that, we find that as long as we stay away from the edges of the plate, that the field inside is nice and uniform and is everywhere perpendicular to the surfaces of the plates. Okay, I'll draw these just to show you that I know, but we're going to ignore the fields at the ends of the plate. We'll stay in the middle here. Okay, so this is the electric field, and the analysis that I did is the same, and I'm going to reverse the charges just so that you can see it. Suppose somehow a positive charge somehow got released from the positive plate. It managed to jump out in the air. How could that possibly happen? Well, one way to do that is something called the photoelectric effect, which is essentially you shine a light on the piece of metal, and the energy the light contains manages to, sorry, I'm trying to line up the picture here. It's not working real well. If I shine a light on this metal plate, the metal absorbs the energy in the light, and if a charge picks up that energy, it can pop out. That's called the photoelectric effect. It's not this quarter. That'll be next quarter, maybe not even then. Whatever. Somehow or other, a positive charge gets popped out, and as soon as that happens, this charge, you can see the electric field. It's going to experience a force that way. It's going to be repelled by the positive plate. It's going to be attracted to the negative plate. And if it starts out with essentially zero kinetic energy, so no, in other words, it starts out with an initial velocity of 0, then it's going to accelerate across the distance between the two plates. And by the time it arrives on the other end, so it'll start out here with v equals initial velocity is 0. Here it'll start out with final velocity is greater than 0. So its initial kinetic energy is 0. Its final kinetic energy is 1/2 mv final squared. Okay, and so the work done is equal to the change of kinetic energy, right? And so it's the same thing. And so if I start it at a position, I'm actually going to move it just slightly closer. If I start at a position that's essentially the location of the positive plate and let it fall the entire separation distance between the two plates, call that distance d, I guess. Right? Then the electric force will do work on it, F times D, and the electric force is Q times E. And so the amount of potential energy, so it doesn't have any kinetic energy here, but it does have potential energy. And the amount of potential energy that it has here is equal to the amount of kinetic energy that it finally ends up with. Again, conservation of energy. And every point, clean this up a little bit. It doesn't really, again, as long as I stay away from the edges of the ends of the plates, every point that far away from the metal plate is going to start out with the charge. This blue charge here, this positive charge, will start out with the same amount of potential energy, no matter where it is on this orange line here. On the other hand, if the charge started out at a distance, and how this happens doesn't matter, but if the charge instead started out this far from the negative plate, then its potential energy would be lower, would be smaller than it was in the case where it started out here. Okay, and it would have less distance to cover, there would be less distance for the force to act, so less work done. Less work done means less change of kinetic energy. Less change of kinetic energy implies a smaller initial potential energy. And so this, again, or these two, both are lines of equal potential energy. And so is this one, and so is this one, and this one. All these orange lines represent possible starting locations for our test charge. And anywhere along each of these vertical lines, the test charge would start out with the same amount of potential energy anywhere on one of the single lines. But the amount of potential energy of this line is different from the amount of potential energy of this line, which is different from the amount of potential energy of this line, and so on. Okay? So what I've done then is set up a situation sorry. What I've done is set up a situation in which I can, or for which I can apply the principles of conservation of energy. And if you remember some of the studies of conservation of energy in your first quarter, studying mechanics and so on, a lot of physical problems that are difficult to handle using Newton's laws and conservation of momentum or whatever else turn out to be quite simple using conservation of energy as a problem-solving strategy. And the same is going to be true here. And so that's what I'm going to do. And so my next goal is to come up with a mathematical expression for the potential energy of the test charge when it's inside an electric field. That'll be next.